So we're going to continue where we left off yesterday, and today we're going to make a focus on transformations of rational functions. So with transformations, we start with our basic rational function, 1 over x, and then this function becomes transformed by putting all of our transformations in it. So I'm going to say g of x is equal to, so normally if you remember, wherever the x is becomes my inside of my function. Wherever the outside is becomes my outside. So right there and there. So I'm going to write 1 over, and I'm going to put a bracket around here. And then my plus k for my vertical translation goes on the outside. My a, which is my vertical stretch by a factor of a about the x-axis, or my reflection in the x-axis would be the a variable. And then my horizontal stretch by a factor of 1 over b. And then my horizontal translation, h units left or right. And then my reflection is also contained in my b variable. So basically, we can have our transformations like this. But in this case, because my b variable and my a variable can sort of be combined, and we can sort of get the same graph using a vertical or horizontal stretch, we are going to focus on our transformed function being g of x equals a over x minus h plus k. And we're going to kind of eat up the horizontal stretch by combining it with the vertical stretch. So we combine all of the stuff in red together, and we kind of pull it all together and treat it as a vertical stretch and a vertical reflection. So in this example, my a, just like in transformations, would represent my vertical stretch by a factor of a about the x-axis. Now again, I want this a to be strictly positive because we don't say that the stretch is negative. So if a is negative, we know that there's a reflection in the x-axis. And that's because the negative would sit on the outside of the function. Now, the x minus h part of my expression, that's still referring to the function moving left or right. Again, depending on the normal rules we've learned. So if I see an x plus a 3, that would mean a horizontal translation 3 units left. And if I see a x minus 3, then I would know a horizontal translation 3 units right. And then just the same rules that we're used to for our vertical translation. There's a vertical translation up k units or down k units depending on the sign of k. So basically what we're going to do in these examples is we're going to pay attention to the transformations in these formats because most of them get embedded in these formats. So they say sketch the graph of this function. How do I know it looks like a transformed function? Well, my normal starting graph is 1 over x, and then I sort of have a term that's being added or subtracted. The stuff we did yesterday was with everything like a polynomial divided by a polynomial. So if I were to make a common denominator and do 6 minus 3 bracket x minus 2 over x minus 2 and clean that up, so minus 3x, minus 3 times minus 2 is plus 6, so this would be a plus 12 over x minus 2. If I simplify the function, I can treat this as the stuff we did yesterday with analyzing rationals. So you can kind of treat it like the stuff from yesterday, but it's almost easier to treat this stuff like the stuff we're going to do today and treat this as transformations. So first thing I want to do is I want to state my transformations. So there's a vertical stretch by a factor of 6 about the x-axis. we have a horizontal translation 2 units right, and then a vertical translation 3 units down. Now what we're going to do is we're going to compare this to our normal graph that we're used to, which is our typical rational function, which had a branch here and a branch here. So my normal horizontal asymptote would have been 0, and my normal vertical asymptote would have been 0 as well, and now we're going to transform these. So if I do a vertical stretch by a factor of 2, doesn't affect x coordinates, horizontal translation 2 units right would pull my horizontal asymptote to positive 2. A vertical translation 3 units down and a vertical stretch by 6. 0 times 6 is 0, and then I'm going to move my horizontal asymptote 3 units down. So I'm going to plot these points. 1, 2, 3. So there's my horizontal asymptote. Y equals -3. I plot my horizontal asymptote. X equals 2. And then literally my graph is just going to be kind of shifted into those two branches with no stretches, no translations. So you could take points. One of the points on my original function that we learned from yesterday off the table of values was -1 and 0. That is, we're going to change, or sorry, not -1 and 0. When x is -1, y is -1 over -1, which is -1. And then that would get transformed by a vertical stretch by a factor of 6. So that would multiply that by 6. And then 3 units down. And my x coordinate would just be moving 2 units right, so -1 plus 2. And that would be the new coordinate 1 and -9. So when x is 1, 4, 5, 6, 7, 8, 9. So we kind of know my branch is going to go towards that x-intercept, or sorry, that vertical asymptote, and go through the point and get towards my horizontal asymptote. We know that's what the branch looks like. Now you'll notice I slowed down a bit because what I did was I looked at the y-intercept of this graph, and my y-intercept would have been sub in x is 0. And so -3 minus 3 is -6. So if you saw me slow down right there, it's because I was kind of analyzing the y-intercept, so I had another point to go through. And then what I'm going to do is I'm going to draw the other branch of my graph, but I would also need to find my x-intercept to be able to do that. So if I look at this function kind of in this format, when x is 4, my numerator would become 0, and then I can go ahead and just draw that in and do it like so. So what I would do is I would put this in my calculator and just help me use table of values to make sure my graph gets accurate. But other than that, we knew that the branches were going to do that because these original branches had done the shape like this that we already knew. We just need to have a little bit of accuracy when we draw it. Okay, let's state the domain. The domain is the set of all x such that x is not allowed to equal +2, but x can be any real number. In this case, I have a vertical asymptote at -3, and the graph is not crossing the vertical or the horizontal asymptote. So my graph is y such that y cannot equal -3, y-er. And then they ask for equation of asymptotes. So this is my new vertical asymptote. I'm just going to circle it. My new horizontal asymptote, circle it. My domain and range is being asked of me. And my end behavior and NPV behavior. So as x approaches my NPV from the right, y approaches. So as x approaches 2 from the right, my y's are going up to +infinity. As x approaches 2 from the left, my y is approaching, and this part of the function is going down, so -infinity. So that's my NPV behavior. And my end behavior, as x approaches infinity, as x approaches minus infinity, what's happening to my x and y values? This part of my function is going towards the horizontal asymptote, and so is that one. So my y is approaching -3 in both scenarios. This is good because this is typical horizontal asymptote behavior. And over here, this is typical of vertical asymptote behavior with the NPVs here. Okay, and then there's my information. So all I'm doing is approaching the problem using transformations instead of using the analyzing rationals that we did yesterday. Now, if I were going to do the analyzing rationals, I would probably want to factor this, and you can more clearly see that the x-intercept is 4, which is how I knew to quickly put my x-intercept at 4. Okay, so if I give you a over x minus h plus a k, we basically have transformations, but you can approach the problem whatever method you want to approach it. Now in this example, they give us the graph and they want us to find the equation. So I'm going to write down my characteristics and then just put them in. I know that this is a transformed function because it can follow the format a over x minus h plus k. It's a very simple graph, but you can also use the skills you learned yesterday to try to approach it as well. Now this horizontal or vertical asymptote is at x equals -3. So the factor for that would be x plus 3. So that would sit on the denominator of my expression plus k. And then my vertical, not my vertical, I keep saying the wrong words today. My horizontal asymptote is at y equals 0. So that would sort of be my k value over here. So y equals a over x plus 3. My k is plus 0. That's my horizontal asymptote. And then I just literally need to take a point like we've done in the polynomials unit and solve for the a value. So I'm going to take this dot that they give me, which is located at 2, -2, 1, and I'm going to sub in that point in order for me to be able to solve for a. So 1 is equal to a over -2 plus 3 plus 0. 1 is equal to a and plus 0. So a is just equal to 1, and then I'm okay to write my equation 1 over x plus 3 plus 0, which would be finally this graph right here. So this is just telling me my graph had moved 3 units left from where it would normally sit. Now, when you're given a question that is sort of polynomial divide by polynomial, this sort of looks like yesterday's lesson where we were analyzing rationals, but it doesn't sort of fit into the transformation format. So what I want to do in order for this to fit in the transformations format is do a little bit of long division or synthetic division. So here's my divisor. I'm going to write it as a root because I'm going to add. So I'm going to take the divisor, use the root, and then I'm going to write my coefficients in descending order. So 4x minus 5. I carry down the 4. 4 times 2 is 8. Minus 5 plus 8 is 3. So I'm doing long division to do the division statement for this expression. So 4x minus 5 over x minus 2 is equal to, this last box represents my remainder, my quotient is 4 plus remainder over divisor. And I get an expression that looks like this. So my y function is 3 over x minus 2 plus 4. And now it looks like the format of above that I can describe transformations. So it asks us to describe the transformations: vertical stretch, by a factor of 3 about the x-axis. That's my a value. My h value is positive 2, so I have a horizontal translation two units right, and I have a vertical translation four units up. So there's my information. It asks us to state the asymptotes. So my vertical asymptote, based on yesterday's lesson, is coming from my denominator, x equals 2. It's coming from right here. My horizontal asymptote is coming from my k value over here. So my horizontal asymptote is y equals 4. It asks us for the intercepts. So my x-intercept is set y equal to 0, solve for x. I'm going to subtract 4 on both sides. Multiply both sides by x minus 2, minus 4x plus 8 equals 3, and then solve for x. Minus 8 on both sides, I get a minus 5. Divide by negative 4 on both sides, I get a 5 over 4. So my x-intercept is 5 over 4, comma 0. My y-intercept is going to be, I'm going to set x equal to 0. So this is y equals negative 1.5 plus 4. So y is equal to whatever 4 minus 1.5 is, 2.5. So my y-intercept is 0, 2.5. And that's the end of that problem. So the tricky part of this problem is recognizing you have to do synthetic division or long division to get it into the transformation format. Again, in a given question, when it's a diploma or when it's our assessments, it doesn't really matter what format you do it, but if I ask you transformations, you sort of want to show and highlight your transformations knowledge, but as the diploma nears closer, you can use whatever technique you want. Now I'm going to, again, do long division. So I'm going to use the subtracting format this time, just for the people that like subtraction. And hopefully I don't make a careless mistake. So I take the factor, I take my coefficients in descending order, carry the 2 down. 2 times negative 4 is negative 8. I subtract. 2 minus negative 8 is 10. I box that in, that's my remainder. So I'm going to write my division statement. 2x plus 2 divided by x minus 4 is equal to my quotient plus my remainder over my divisor. Okay, so my formula or my function that I'm looking at in the a over x minus h plus k format looks like this. So let's describe what's happened. Vertical stretch by a factor of 10 about the x-axis. Horizontal translation four units right, and then a vertical translation two units up. Let's go ahead and write the characteristics we know. My vertical asymptote is coming from the one I'm going to highlight it the same way I did on the other side. The red piece, which is x equals 4. My horizontal asymptote is coming from the k piece, which is y equals 2. We can find my x-intercept by setting y equal to 0. 0 equals 10 over x minus 4 plus 2. And now I'm going to go ahead and solve for x. Minus 2 is equal to 10 over x minus 4. I'm going to go ahead and multiply both sides by negative 2. I'm going to subtract 8 from both sides, so minus 2x is equal to 2, and then divide by negative 2, which means I get an x-intercept of negative 1 and 0. To find my y-intercept, again, algebraically, I'm going to take my equation, sub in x is 0 this time, and solve for y. 10 divided by negative 4 plus 2. And that gives me negative 1/2, so negative 0.5. So my y-intercept is 0, negative 0.5. And that's like pretty much the lesson. There's not a lot going on with transformations that you don't already know, so it tends to go a lot quicker. Key ideas is that the denominator represents your vertical transformation, vertical asymptote. Your k value represents my horizontal asymptote. Another key idea is if you take the original equation in a transformed format and simplify it, you can treat it as the same as what we were doing in the lesson from yesterday, which is analyzing rational functions, kind of using all of our NPVs, PODs, and all that jazz from yesterday. But again, transformation's super straightforward because it is, again, a repeat of what we've already done throughout the whole unit. What I would recommend, again, is studying for your polynomials test tomorrow. So just practice your synthetic division, long division, remainder theorem, factor theorem, and then all of the graphical characteristics of polynomials.